Lesson 7.4, geometric sequences. So a sequence is a set of numbers that has a particular order or pattern to it. Arithmetic sequences, you guys saw back in, I think it was module two, they looked a lot like linear equations. And you start with some A1 value and then you add some difference value, like 1, 3, 5, 7, 9, right? There's a pattern there, right? You're just adding two every time, right? A geometric sequence is we're going to multiply by something, right? So like 1, 2, 4, 8, 16, 32. I'm multiplying by 2 every time. That would be more like one of these guys. Okay? There are different formulas you can apply. So in this class, almost all the time, we apply these explicit formulas. So if you want to figure out the nth term, like what's the fifth term or the 10th term, the 20th term, you have some formula, you just plug in whatever number you want for x or n, right? And then you find like the y value or that value, right? Uh, but there's this other way to write a formula. It's kind of no, we almost never do this one in this class. It's called recursive. And what recursive is you take the previous value and you do something with that, right? So a sub n equals a sub n minus one, like the previous value, and then you push it through some formula, maybe multiply it by something or add something or something like that. Okay? Um, actually, here it gives you guys an example of um, some examples of these, right? So arithmetic sequence, there was some common difference from term to term, like A1, A2, A3, right? But the geometric sequence, there's some common ratio, right? So if you keep multiplying by 2, 1, 2, 4, 8, 16, the common ratio would be 2, right? Explicit formula lets you find the nth term like A sub n as a function of n, so you could just plug it in, just like a regular formula, nothing great, right? Recursive is the one that you almost never see. Here, I'll write this so it shows up a little bit bigger on the screen, but recursive formula is like the nth term, right? So a think of it kind of like y equals something, right? And n could be it's usually a discrete like term number 1, 2, 3, 4, 5, 6, 7, okay? Is equal to now. Well, okay, if it's geometric, then that's what this R is for, right? Actually, I can call this what they call it up here, the common ratio. Common ratio, not to be confused with interest rate. This is different combination here, times a n minus one. Okay. This a n minus one bit right here is the previous term, right? Or the term before n term. So if they say like, find the 10th term, well, this a n minus one would represent the ninth term, whatever that is. Yeah. That. Uh, Recursive formula. Okay, let's go ahead and jump into the book examples, okay, and then we'll do some textbook questions. Okay. Example one. Example one. Yeah, whatever. Determine whether the sequence is, I guess, arithmetic or geometric. So let's write these numbers down. So we got 2, we got a 6, we got a 15, we got a 30, dot, dot, dot. Okay. So what's the pattern here? Now, if I thought it was arithmetic, I'd say, okay, well, let's see, 2 plus 4 is 6. Looks like I'm adding 4 maybe, right? But then if you add 4 to that, you only get 10. That looks nothing like that. Okay, so it immediately falls apart. So hey, let's try multiplying. If I do 2 times 3, that gives me 6. And then 6 times 3 is 18. Right? So okay, so that didn't work either. You know what? This is going to be neither. Ratios are not the same. Oh, okay. All they're looking for is not geometric. Okay, whoops. Okay. This is neat. No, not geometric. Okay, so it failed the arithmetic test by trying to add, but it also failed the geometric because I would say, oh, say times 3. Hey, can I do that again? Times 3? Oh no, and then it failed. Right. Oh, okay, so that didn't work. So let's just keep going. Example 2. Okay, I've got to find one that works. I can show you how this works, right? Find and graph the first 6 terms of the geometric sequence. So they give you -1, comma, -2, comma, -4, comma, dot, dot, dot. Now they do tell you that it's geometric. So it looks like I'm just multiplying by 2. So times 2, times 2. Wait. Okay, and then you can just repeat that process. You can keep going. Okay? So if the first term, I'll call it A1, it looks like it's -1. Okay? The second term, well, they gave me that, and they also gave you the third term. Okay. But let's keep going. Let's go A4, A5, and A6. That'll be the fourth, fifth, and sixth terms. Okay. So just keep multiplying by 2. So this times 2 is -4 times 2 is -8. That times 2 is negative 16. That times 2 is negative 32. Right? So that'd be it. Okay, actually, no, they graphed it for you already. You got like this, looks like a plot, right? Because remember, with all these sequences, we're looking at individual discrete points. You guys do see these are discrete points. So we got the coordinate 1, negative 1 right there, bam. 2, negative 2, bam. 3, negative 4, bam. 4, negative 8, bam. 5, negative 16, bam. And 6, negative 32, bam. It's right there. Okay. So yeah, they graphed all of them. Graphed all of them. Okay. Now I wonder if we could come up with uh, formulas for these. Okay. So what is the nth term equal to? Well, I think it's you take the first term, so I'll say A1, okay, and multiply by the ratio to some power, okay? But the power I'm going to do n minus 1. So whatever the nth term is, I'm going to subtract 1. Okay? And watch why this is going to work. I'll show you guys some examples. So like the first term, for example, in the first term, let's go ahead and plug in right here. Okay, actually, I'll say a sub n equals negative 1 times, and then for r, well, that's this 2 right here, goes in for that r times 2 to the n minus 1. Okay? Or you could simplify it like this. So negative 1 times negative 2 n minus 1. Okay? Okay, so I think this would be a good, I'm going to write this as explicit formula. Okay, but let me show you guys this does work. Okay? So with the first term, if I plug in 1 for n, that's 2 to the 1 minus 1. 1 minus 1 is 0. 2 to the 0 is 1. So, and it's negative, so it comes out to negative 1, which matches this. Okay? Let me try something else. Let me try how about the fifth term, which I know should be negative 16, but we're going to put it through the test. So in the place of n, what if I put 5 for the fifth term? So I got negative 2 to the power of 5 minus 1. Okay, 5 minus 1 is 4. So that's 2 to the power of 4. 2, 4, 8, 16. This would be 16. It's negative. Negative 16. Yeah, which is exactly what I got by just doing it by hand, just one trial at a time. Okay. And so, okay, so now you can see something about what an explicit formula would look like with these sequences, right? Which is that there's some initial value, some starting value, right? You plug out here, right? And you can multiply by the ratio to the power of whatever term you're on minus 1. Okay, so that'll feed into that formula. So test it, that works. Okay. Now, another type of formula your book talked about was recursive. So what would the recursive formula look like? And the recursive, here, let's spell this out. Recursive formula would be like, I'll say A1. So I'm going to name the first term as negative 1. Right, so we got that. Okay. And R equals 2. Okay. So regardless of what term you're on, right, like A sub n equals 2 times A n minus 1. Okay. So put these ideas together. Okay, this 2 actually becomes that 2 idea. That's where I got that from. Okay. So the recursive formula is that whatever the term is, just take the previous term. That's what A n minus 1 is. This is the previous term, right? And multiply by 2, and that'll give you the new term, right? And if you like, you can note also where to start from. Okay. So these are two different ways of describing the sequence, two different ways of doing it. The explicit way, which is normally how we think of it in this class, but also this recursive way. Okay. Example 3. Chocolate. Javier wants to eat less chocolate each day. To achieve this, he decides to start with a 50-gram bar of chocolate and eat half of it the first day, half of what's left the second day, and half of that the third day, and so on. Right, so maybe he has this chocolate addiction and he doesn't want to go cold turkey, so he buys one more Hershey's bar. I'll draw that for you guys. Here's a Hershey's bar. Okay. Says, okay, I'm going to make this last as long as I can. What I'm going to do is, yeah, I know I'm a complete chocoholic. So on the first day, I'll go ahead and eat half this chocolate bar. So I just hash that in. Okay, so you just ate all that. That's day 1. Day 1, he eats half the chocolate bar. Okay. Okay. Which means he has half of it remaining. So on day 2, he's going to eat half of that. So hash that in. Nom, 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 nom. All right, there's day 2. Right, he's like weaning himself off the chocolate. Okay. Day 3, he eats half of what's remaining, which is this hashed bit right here. Okay, so here's day 3. Okay. Day 4, he gets half of what's remaining there. So here's day 4, right? And this could keep going on and on, right? So maybe then he splits this in half, and then that in half, and then that in half, and then that in half. Okay, so it could just keep going. Okay. Um, right, okay, and the whole thing started off as 50 grams. Javier starts on Monday. What is the mass of the piece that he will eat on Friday? There we go, Friday. Okay. So we could just count day by day, right? So we could do it that way. Okay. So I'll say, let's go. I'll spell out the days. Monday, Tuesday, Wednesday, Thursday, Friday. Okay. Friday. I'll call Monday A1, Tuesday A2, Wednesday A3, Thursday A4, and Friday A5, like the fifth term of the sequence, and that would get the answer to us. Okay. Well, A1 looks like he ate half of the 50-gram bar. The whole thing's 50 grams. He ate half of it. That would have to be 25 grams. Right. And then the second day, well, he has the 25 grams remaining, and he eats half of that. That's like 12.5 grams. Okay. Next day, he eats half of that. Here's the calculator here. So 25 divided by 2, of course, is 12.5. Then all I have to do is hit divide by 2. And actually, the calculator is already thinking sort of recursively. Like every time I hit enter from now on, it's just going to take the previous answer and divide by 2. Okay. So 6.25 grams. A4 Thursday is eating 3.125 grams. Okay. And Friday, one more halving, 1.5625 grams. Okay, now this is extremely precise. So, okay, maybe like 1.56 or whatever. I mean, you could cut off the decimal at some point, reasonably speaking. Okay, but there you go. So the fifth day, it's the fifth term, A sub 5, okay, it comes out to that in grams. Okay. Now we just did it by hand, right, step by step by step. Okay. But could you come up with a formula for this? Let's do an explicit formula. Explicit formula. Okay. So I can say that the amount of chocolate he eats on the nth day, okay, of course we're targeting day number 5, but let's say the nth day in general, is equal to whatever he ate on the first day times the ratio, common ratio. Is that what they put the formulas back here? Um, yeah, common ratio to the power of n minus 1. N minus 1. There we go. Okay. So what he eats on the nth day, well, I know the first day was what, 25 grams? 25 grams. So I'll put that in for A1. Okay. And then times, no, this ratio keeps being half, 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 half. So R is 1/2. And it's raised to the n minus 1. Right. Why minus 1, by the way? Because this first term, like if you were to translate this back into a proper linear equation, it wouldn't properly be the y-intercept. It'd be like wherever x is equal to 1. So it's kind of like the whole graph is shifted from our traditional equations. Right? So this should be it. Now, if I plug in 5 for n, what is a of 5? Okay, I mean, it's got to be this number. I just want to show you guys this is going to work. So let's do 20, take the 25 grams that he ate the first day, multiply by 1/2 to the power of, now, n minus 1. So in parentheses, we'll go 5 minus 1. Okay, so the day, yep, it's the same thing, 1.5625. All right, that's grams, which matches that. Ding, same thing, same thing. Okay, so there's an explicit formula to tell you how much on any day, how much chocolate he's going to eat. Example 4. Write an equation for the nth term. Okay, well, that's just what we've been doing. Been providing some extra examples for you guys. Example 4. Yeah, so let's do this. Okay. So they give us -1, comma 3, comma -9, comma 27, comma dot dot dot. Okay. Now, one thing right away, do you guys see how from term to term it's flipping sign, negative, positive, negative, positive? Okay. Well, that tells me we're probably multiplying by some negative value. In fact, it looks like it's -3, isn't it? Times -3 times -3 times -3. Every time you multiply by a negative, it swaps the sign. Okay. So, okay. So it's gotta be like that. Now, I think my A1 is -1. My common ratio is -3. Right, so if it's like, I know that a sub n equals a sub 1 times r to the n minus 1. We've just done a few of those so far. Right? So I think all I have to do is pop all the pieces into this expression. So a sub n equals, okay, take my a sub 1, which is negative 1, multiply by this ratio, which is negative 3, all to the n minus 1. Okay. I think that's the explicit formula I need right there. This is my explicit formula. Right. Did your book just go explicit? Um, well, got here. It kind of did that here. I think so. I'll just test my or check my work here. Let's check this work. So I think the fourth term should be positive 27. So if I plug in 4 for n, do a sub 4, where the n goes, I'll put 4. I should get 27 out of this. Let's see if I do. So go negative 1 times and then negative 3, all raised to the power of 4 minus 1. Right, and I've got to get 27. Yeah, sure is. It's 27. Check. It's that and that match. So we are good. This formula totally worked. Okay, so they do a couple more like that, but it's basically the same idea, looks like. Example 5. Right, now I'm seeing I'm talking about recursive, right? Recursive and explicit formulas. Example 5. Okay. Given a formula for a geometric sequence in recursive or explicit form, translate it to the other form. Okay, so it looks like they start out with recursive, hence they went explicit, and then question B is the vice versa. Right, so let's try this. So part A, they're telling us the first term is 5 and that the nth term is 1/5 of the previous term. Remember, a sub n minus 1 is the previous term, right? Oh yeah, I forgot to mention this earlier. But normally you see this tag onto the end. N is greater than or equal to 2, right? Because n equals 1 would count for the first term. So it's like, well, we haven't really done anything yet. Just give it something, right? So you do have to get to the second term before you're really allowed to start applying things in, right? And this is called recursive formula. Right, that's what this is right here. Right, this right here is recursive form. Well, I guess including the n minus 2. That's part of it too. Right. But can we make this explicit? Make this explicit. Well, we've done a few explicit formulas so far, so let's just put it in this form. So the nth term will be the first term times the common ratio to the n minus 1. Okay? So the nth term is, well, the first term they gave us right here. So that's 5. The common ratio looks like 1/5. That's like right here. So 1/5. And then n minus 1. Like that. There you go. There's explicit formula. Point explicit. Okay. Okay, so for example, if the first term is 5, then every term after that you're just dividing by 5. I think the second term would be 1. The third term would be 1/5. Third term would be 1/25. Here, let me write this up. So let's go 5, comma 1, comma 1/5, comma 1/25. The next one is 1/125. We just keep dividing by 5. Okay. Is my explicit formula consistent with that? Let's see. So 5 times, then 1/5 is 0.2. It's the same thing. Okay. Raised to the power of, let's see, 1, 2, 3, 4. My fourth term should be 1/25. Which is 0.04. Let's see if it is. If I plug in 4 minus 1, 4 minus 1, see if I get 0.04. Yeah, it is 0.04, which is 1/25. So check out. Check. Bing. That works. Okay. All right, now, example 5b, we're going to go the other way. 5b, we're going to take something that's explicit, which is the nth term equals 2/3 times 7 to the n minus 1. Okay. And we need to make this recursive. So it'd be the same expression, just a different way to think that, or I should say a different way to explain the same sequence. Okay. Well, we can use this model right here. Right? So I need to name the first term. So I'll say the first term is equal to, it looks like it has to be 2/3, doesn't it? Right? Like here, if you plug in 1 for the first term, 1 minus 1 is 0, 7 to the 0 itself is 1. This goes away. You just get 2/3. So the first term I know is 2/3. So that's 2/3. Okay. I know the common ratio has to be 7. Looks like we're keep multiplying by 7. Okay. Okay. And so the nth term would be 7 times the previous term, 7 times a n minus 1. Okay. And then I'll do comma, n is greater than or equal to 2, because you have to get to the second term before all this kicks in. Okay. So I think these two parts together are the recursive formula collectively. Okay. So I'm telling you the first term, and then I'm saying whatever the previous term is times 7, that'll give you the next term. Okay. Okay, so this is explicit, this is recursive, and they'll both give you the same sequence. Sure. All right. Right, last example 6. Geometric means. Example 6. So find 4 geometric means between 243. So blank, 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 and 32. Right, geometric means. Okay. And there's a process they'll tell you to do here. Right. Well, you know this explicit formula we've been using. The nth term is equal to the first term times the ratio, and then n minus 1. Okay. And we know that how many terms I got here. I can just count them out. 1, 2, 3, 4, 5, 6. Because if there's 4 terms that go from here to here, right? This is a geometric sequence. Right? It's going to follow this form. Okay. If I let A1 be 243, so right here I'm going to put in 243 for my first term, okay, and I let the 6th term be 32, then I can solve for this R, this common ratio. You see how I did that? Right? Say, hey, for this n, let's plug in 6 because I'm going to 6 terms, and I know what that term is. It's 32. Okay, so now I can solve for R. Right? So let's do 32 out of 243 equals R to the, and 6 minus 1 is 5, R to the 5. Right? What is 32 over 243? Do these have some, is there some better way to say, oh, I know what this is. Right. Guys, 2 to the 5, 2, 4, 8, 16, 32 is 32, which looks like that. 3 to the 5, let's see. Okay, 3 to the 5 is 243. Yeah, that's what it is. Okay. So if I take each side to the power of 1 over 5, 1 over 5, 1 over 5, then I can solve for R. Okay. So R is equal to, comes out to this right here, 2/3. Right. Okay, so there you go. Okay. Right. And now that you know that the common ratio is 2/3, I'm just going to take my A1 value, my first term, and just keep multiplying by 2/3. It just recursively, you could think of it that way. 243, comma, right. Just keep multiplying by this 2/3 over and over again. It should fill in all these blanks and it should be exactly aligned with the 32 by the time we get to the sixth term. So times 2 over 3. So that's 162. And then enter. Just keep hitting enter. Right. Okay. And then if I hit enter one more time, the calculator has to say 32. And I know everything aligns, it all works. Yeah. All right, there you go. There you go. Okay. It says, where are we supposed to find the 4 geometric means? Oh, there it is. It tells the answer right down here. Right at the bottom of the page. It says the answer is 162, 108, 72, 48. Yeah, that's exactly these 4 middle values I got right here. Okay. All good. All good. Okay, jump into the book puzzles. At page 33, determine whether each sequence is geometric. So number 1, 5, comma 7, comma 9, comma 11, comma 13, comma dot dot dot. Okay. I think this is not geometric. I think this is rather arithmetic. So it is a sequence. It's just an arithmetic sequence, which goes back to module 2. Okay. So I could say that the nth term is equal to the first term, which in this case is 5, right? Plus, and then the common difference is 2. See how I just keep adding 2, adding, right? 2, and then that's multiplied by n minus 1, right? We did this a long time ago, right? So this is not geometric, this is arithmetic. Let me test this. Does this work? So the first term, 1 minus 1 is 0. The series out gives you 5. Yep. How about the second term? 2 minus 1 is 1 times 2 is 2 plus 5 is 7. Yep, that checks out. Okay, so that checks out. Okay. So arithmetic, not geometric. Number 2 looks like 3, comma 6, comma 12, comma 24, comma 48, comma dot dot dot. Okay. Ah, now this one I'm saying times 2, times 2, times 2, times 2. Yeah, from term to term it keeps doubling. So it looks like A1 is equal to 3. The common ratio is equal to 2. So factor 2 keeps doubling. Okay? So I think the nth term is going to be the first term times the common ratio to the power of n minus 1. And oh yeah, this would be yes, it is geometric sequence. Right. Let me test my work here. So like the third term should be 12, right? So let's do 3 minus 1 is 2. 2 squared is 4. 4 times 3 is 12. Yeah, it lines up. Aha, it's good. Good, good, good. 13. Family. Amanda is researching her ancestry. She records the names and birth dates of her parents, their parents, and so on in an online research tool. If she can locate all the information, how many names will she have to record 5 generations before her? Okay. So we could draw this out, make like a giant family tree, and then we could apply a math formula to this. Okay. So here, let's put Amanda at the top, and here I'll go backwards in time down the page. Let's do that. Okay. So here's Amanda's mom and Amanda's dad. Okay. Biological mom, biological dad. Okay. And then, okay, so how are we getting past? It says 5 generations before her. Let's count her as generation 0. And then this I'll call generation 1, as in 1 generation before her. Yes, that's the way I'm going to interpret this. Okay. Right, and then her mom has a couple biological parents, so does her dad. So it gives her, maybe I'll represent this with stars. 1, 2, 3, 4 grandparents. Okay. And then each of her grandparents had a couple of parents. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so her grandparents, I'm going to call generation 2, as in 2 generations back. Her great grandparents, generation 3. Okay. All right. And we still need to go 2 more generations, which would be kind of a tight squeeze on this paper. Right? But you can see the pattern. Right? And this whole lesson is about geometric patterns. And this is a geometric pattern. So let's look at the formula we're going for. So an explicit formula. So the nth term could be the first term times the common ratio, and then n minus 1. That's what we're doing. Okay. Now, generation 1, I'm going to call like the call this first term here, which is going to be like 2 because she has 2 biological parents. So that's where this 2 is coming from. Okay. Now, this R comes the fact that every individual has one biological mother and father, which is 2 people before them, then n minus 1. So this could give you the nth term, right? So however many generations back. Now let's test this formula and then we'll go plug in 5 for n so we can actually get the answer. Okay? Now I'm claiming that if you go 1, 2, 3 generations back, she has 8 great grandparents. You guys see that? 8 great grandparents. So if I plug in 3 for n, I should get 8 great grandparents. Let's see if I do. So okay, 2 times 2 to the power of, and then let's go 3 generations back and then minus 1. Do I get 8 out of this? Let's see if I get 8. Yeah, I do. 8 grandparents. Okay. So if I want to go back 5 generations, all I got to do is plug in 5 where that n is. To the 5 minus 1, which is, okay, so I scroll up, scroll over. Okay, so I plugged in 3 just to test this little family tree here. Let's go all the way back 5. That would be 32. And that would be, let's see, this is grandparents, great parent, great, 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 great. So this is great, great, great grandparents. Okay. Right? So there you go. There you go. 14, Moore's Law. Ah, this one here, I'm gonna pull this here. This one I have an infographic of. I think I showed you guys this the other day. Right? This is the number of transistors you can economically fit on a computer chip as a function of the number of years time by. Now, this number of years is scaled linearly, 1970, 72, 74, 76, 78, so on, all the way up to 2016. Every one of these dots is a commercially released computer chip. So let's say back in 1991-ish, looks like there were these couple of computer chips that were released, right? And they're named here, right? Right, and if you stand back and look, say, okay, it looks like a straight line, right? Okay, so we can fit more chips on a computer every passing year. There's more, right? More transistors on a chip. But if you look really close, do you guys see that the vertical axis is actually scaled logarithmically? Right? So sometimes it's called like a semi-log type curve, right? So this goes 1,000, 10,000, 100,000, a million. Right? So it's going up by factors of 10. Okay? Now, if you had scaled the number of transistors also linearly, right? So it went like 1, 2, 3, 4, 5. This all these points would actually be best represented by an exponential curve. It'd actually like take off like that, right? Exponential curves are kind of hard to fit to fit on paper and make sense of, right? That hence we're doing a semi-log curve with this because lines up and it's easier to interpret, right? But that's what Moore's law is. Moore's law, yeah, is exponential growth. So it would fit perfectly in this module. Okay. And according to this, it says the number of transistors you can fit on, say, a square inch of an integrated circuit of a computer chip would double every 18 months. Right, so double it every 18 months. So every 18 months, go times two, times two, times two. Yep, it's definitely a geometric sequence type. Assuming this is true, uh, how many times as many transistors would you expect in year six? Year six. Okay, so we're gonna go forward, say like 6 years. So 14, Moore's law. Okay. So A sub n equals A sub 1 times common ratio to the n minus 1. Okay. So for the 6th year, it's A1 times, okay. So we're doubling. You know what? It says double every 18 months, doesn't it? I didn't think about that, but we're gonna have to get a little tricky, right? Because years, I guess there's two ways we could approach this. We could figure out what the common ratio is year by year, or we could alternately have this n represent sections of 18 months, and year six would actually come out to some different section. Let's do it that way, which I think is a little easier. Okay. So let's say, right, so one doubling is every 1.5 years. Okay. So two doublings would correspond to 3 years. Three doublings corresponds to 4.5 years. And four doublings corresponds to 6 years. See, I'm just adding every 18 months would be a year and a half. That's where the 1.5 comes from, right? Okay. So if I do it that way, then when they say at the end of year six, we're really talking about four doublings. Okay. So this is a different way to think of it. Think about it. Right? Yeah, so you have to reconcile, right, months and years and doublings. Okay. And this is one way to do it. Okay. So we'll take R to be 2, but then N would not, for 6 years, N is not actually 6. It's actually four doublings. Right. So like that. Four doublings. Did I do? Um, actually, actually, I let me rethink that because if I subtract one, that would actually subtract 18 months worth, wouldn't it? Okay. Let me do it the other way. I think the other way is actually better. Yeah. Okay, here. I paused the recording and came back. I'm gonna think about this one actually a little bit different. Let's think outside the box a little bit. Let's actually start with this. So this is 14, right? Because it's really this, isn't it? Right. So 6 years would correspond to four of these sections of 18 months, which corresponds to four doublings. So if you just think of it from that, you can get doubling four times 2, 4, 8, 16. The answer is 16. Right. That's why I just checked the teacher's edition too, and the answer is 16. Right. Now, the other way of maybe solving this which is to say, like if I really wanted to force this type formula on it, right, this here, ignore what I have kind of here, but if I wanted to find some ratio and I wanted to put in terms of number of years, the ratio would not actually be two, it'd be less than two. I got on my calculator, I just kind of did a hand-fisted guess and check, right, until I kind of honed in on 1.74, because if you let that go to the n minus one, then that comes out to something like that, right? Anyway, but if you want to get an exact answer, you have to go through logarithms, right? Okay, so yeah, okay. So this one you have to kind of stand back and see the big picture and think outside the box a little bit. But okay, four doublings would be 6 years, so 16 times the number of transistors you can fit. Okay, number 17. Write an equation for the nth term of each geometric sequence. Ooh, nth term. So it gives a sequence 2, comma, -6, comma, 18, comma, dot, dot, dot. Okay. It's a geometric sequence. So from term to term, see, multiply by -3, multiply by -3 again. Okay, yeah, so that's what we're doing. Okay, so I can say R, the common ratio is negative. Oops, I missed that. Negative. There we go. -3. Okay. Looks like the first term is 2. Okay. So let's try an explicit and then a recursive formula. So let's do explicit formula. Right. Explicit formula. So I know the nth term is equal to the first term times common ratio n minus 1. Right. So we've done that several times. It's been working out. So the nth term could be the first term, which is 2. Right. And the common ratio is -3, and then n minus 1. Okay, let's test this again. So if you plug in 1 for the first term, 1 minus 1 is 0, -3 0 is 1, a1 is 2. Yeah. Next term, 2. 2 minus 1 is 1, -3 to the power of 1 is -3, times 2 is -6. Yeah, you just did. Okay, so it's checking that. 3 minus 2, or sorry, 3 minus 1 is 2, -3 being squared is +9, times 2 is +18. Yeah, it's checking out. All right, how about recursive? All right, recursive formula, I want to name the first term. So I want to say A1 is equal to 2. Right, so you have to name that. So like explicit, it becomes embedded in the expression, but recursive, you want to tell where you're starting. Right? And then I'm going to say the nth term is equal to -3 times the previous term. Right? And then say also uh, n is greater than or equal to 2. Like that. Right? So this would be your recursive formula. Okay, so there you go. There's explicit and there's recursive to each describe the sequence. Let's do another one of those. Right, number 18. So the sequence is 5, comma, 10, comma, 20, comma, dot, dot, dot. And it's a geometric sequence. So it looks like I'm just multiplying by 2 times 2 times 2 times 2, dot, 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 dot. Okay. So you can multiply by 2. So explicit would be the nth term is equal to the first term. Let's go and write in here. Okay. Times the common ratio of 2 to the n minus 1. Okay. Let's test that out a bit here. So put in 1 for the first term, 1 minus 1 is 0, 2 to the 0 is 1, times 5 is 5. Boom. Plug in 2. 2 minus 1 is 1. 5 times 2 is 10. Boom. Plug in 3 for the third term. 3 minus 1 is 2. 2 squared is 4, times 5 is 1. Boom. Yeah, it's all lined up. Okay. Let's do recursive. Recursive, I need to name the first term, which is 5. Okay. I'm going to tell you, so comma. I can tell you the nth term is 2 times the previous term. And the previous term is just a subscript n minus 1. Okay. And then comma, and then one more detail in greater than or equal to 2, because this only kicks in starting with the second term. All right, and that right there is recursive. Okay, so here's an explicit and also a recursive formula to each describe that sequence. Boom, boom. All right, let's do a couple more, and then I think you guys can do any of these. So number 21. Given a formula for a geometric sequence in recursive or explicit form, translate it to the other form. Oh, yeah. Okay. So it looks like they gave us recursive here. They're saying A1 is equal to 3, and then A sub n is equal to 0.6, which was 3/5, by the way, times a minus 1, which is previous term. Okay, and then of course for n greater than or equal to c. Okay. Let's actually list out the sequence. What would it look like? So we got 3, and then if I take 0.6 of that, is that 1.8? Ooh, this is going to look kind of funny really fast, isn't it? So 3 times zero point 0.6 is that, and then times 0.6 is 1.08, and then that times 0.6 is 0.648, and then dot, dot, dot. Okay. So you just keep hitting enter on the calculator, and it just keeps multiplying by 0.6. Okay. Okay. So how about explicit? What would this look like explicit? Okay. So the nth term, if you just want to jump straight to that, is the first term, which is 3, times the common ratio is 0.6, and then raised to the n minus 1. I think this should be the answer right here. I'm going to test this. So let's plug in 4 for n, because I should get this term for 4. So 3 times and then 0.6 raised to the power of 4 minus 1. All right. So fourth term, I should get that. See if I do. Yeah, yeah. Checks out. Bing. Okay. Number 24. 24. Now this one, they gave us the explicit form. Explicit. So we have to go recursive with this. So they're telling us the nth term is negative 2/3 times 6 to the n minus 1. Okay. Now if I write out the sequence, well, if you plug in 1 for n, 6 to 0, 6 to 0 is 1, you get 2/3. Okay, so your A1, your first term is negative 2/3. Negative 2/3. Okay. So now after that, we're going to just multiply by 6. So that'd be 12 over 3. These are all going to be negative, aren't they? Yeah, because 12 over 3 is 4, and that's negative. Okay, and then that times 6 would be 24, still negative. That times 6, got 144, dot, dot, dot. Okay. All right, so let's go recursive. Recursive, I have to tell you what the first term is, which is this right here, then comma. And then the nth term is going to be just 6 times the previous term. Okay. And that accounts for n is greater than or equal to 2. Like that. All right. So, well, yeah, negative 2/3, and then times 6. And then that's negative 4. And then if I say that times 6, boom. And if I just keep hitting enter, boom, I just keep getting the next term. Recursive. Yeah. All right, one more of these. Right. So look at 37 down here. So, yeah, that sounds great. Write an equation to find the nth term of the sequence shown in the graph. Ooh, so now we're looking at this graph. Can I write a sequence, right? Now, so I see a bunch of discrete dots. Everything in this lesson has been discrete pretty much. All right, so 37. Let me list these out. Okay. So I'll do, now I do see that x is increasing by an integer value, or just whole number, because 1, 2, 3, 4, that's all you get. X values are 1, 2, 3, 4. Okay. So the y value could be individual values. So it starts at 56, then it jumps down to 30, then that jumps down to 15. Something's off. Sorry, I don't know why I said 56. This is 60. There you go. That looks better. Right. 60, 30, 15, 7.5, dot, dot, dot. Okay. And no, these are for they're shown on the graph. Right? So let's start with explicit. I'll do it both ways with the guys name. Explicit. Okay. So let's say the nth term is equal to the first term, which is 60, times, and then common factor, looks like we're multiplying by 1/2 over and over to the n minus 1. Here's your explicit formula. Okay. So if you wanted the third term, it should be 15. 3 minus 1 is 2. 1/2 squared is 1/4. 1/4 of 60 is 15. Bing! It works. Okay. Let's go recursive. Recursive. Okay. So I can say A1 is equal to 60. Get that to you. Comma. A sub n equals 1/2 times the previous term. And that's of course for n is greater than equal to 2. Yeah, because you just keep multiplying by half. There's your recursive formula. Explicit, recursive, it's all working. And that is a wrap on 7-4.